We're at an exciting time in the scientific exploration of the universe. Think about it. We have JWST to analyze the atmospheres of other planets. We have the upcoming Titan Dragonfly mission, which is going to fly around Titan, analyzing, looking for pre-organic molecules. We've got missions to Europa that are going to be trying to see if there's any evidence of water underneath the surface of the ice. There's plenty going on. And yet at the same time, this idea of a search for life in the universe is going to be complicated and probably inconclusive. And we've got many examples of when people thought they had found life in the past and when it turned out to not be life. We want to try and avoid that in the future. So my guests today are Harrison Smith and Cole Mathis. They are two astrobiologists who have been deeply thinking about this challenge. And they propose that we're not going to be able to make a lot of progress about whether or not we've found life beyond Earth until we have a better idea of what life really is, before we can definitively search for it outside of our planet. All right, here's the interview with Harrison and Cole. Harrison, give me a quick, one sentence definition of a biosignature. Give me, what's the easiest? If I just look at a telescope and I see something on a world and I know there's life there, what am I looking at?
You asked for one sentence. I think that's really hard. The kind of cleanest answer would be if you could see something that looks like us, something moving around, something that's replicating. Unfortunately, I don't think you'll be able to see those things, though.
Yeah. I mean, the narrative that I've been sort of talking about here on this channel for a long time is that I think we had this overly simplified view of what would be a sign of life on another planet. And as astronomers and astrobiologists look into this, everything that appears to be a signal for life is also a signal from non-life, that you can have methane come from cows and you can have methane come from volcanoes. So it doesn't really help. Do you feel like that we're making progress on this at this point?
I think so, just in the sense that we're getting a better idea of the kind of diversity of processes that life has and kind of what that means in terms of how, outputs of life might interact with natural geological outputs in a planet's atmosphere. But unfortunately, that doesn't kind of close the loop of completely understanding the full dynamics enough that we can say we know kind of all what the unknown unknowns are, for example.
Right. And Cole, you and Harrison, you've sort of, in your new paper, you've termed this idea that you need like a theory of life to better understand. So what do you mean by that?
Yeah, so normally when we talk about a theory of life, we're talking about a theory that we don't yet have, right? So the easiest way to understand it is through analogy. So if I talk about the theory of gravity, Einstein's theory of general relativity is really good. And it tells me, not only sort of what gravity is and what it does, it tells me what affects gravitational fields, mostly mass and energy. And it also helps me understand which things don't affect gravitational fields. So I don't need to know what color Venus is to predict its orbit, right? I pretty much need to know its mass and how far away it is from other planets. And so a theory of life, by analogy, is something that we don't yet have, where we could look at a system and it would tell us, the theory would give us an idea of what life should be uniquely doing that's different from non-life. And what we would need to know to determine whether or not it was alive. So in the same way, we don't need to know Venus's color to predict its orbit. We should have a theory that tells us you only need to measure these things to know whether something's alive. And this has been something that's really been talked about in the astrobiology and origin of life community for a long time. But I think there's been this implicit notion that, well, that's a really hard problem and we should focus on detecting life while we try to sort that out. And sort of what Harrison and I are trying to point out is like, yeah, it is a hard problem, but we might not have a choice in sorting it out if we actually want to detect life.
I mean, I know that when you ask different people, what is your definition of life, you get different answers. Is the astrobiological community starting to agree upon even just like you could point at a thing and go, that's alive, and point at something and go, that's not alive? Are we there yet?
I wish we were, but we're not. I think we're going to keep having this conversation for a long time. And there's been, again, this is related to the problem of theory of life. It's a really difficult problem. And there's been a lot of really good work, both in science and philosophy, about why this problem is so difficult. And really it's a question of like, is life and non-life sort of a natural kind in the way that we could say like liquids and solids sort of represent like a natural kind, something true about the structure of reality. And we don't know if that's the case yet or not for life and non-life. And if it's not, then our search for life is going to be much more difficult. We might have to challenge some basic conceptions about science that date all the way back to like Aristotle.
Like if you were going to come up with some concepts that you would say, well, these are possible indicators of life, what are some of the things that it does?
So one of the focuses of our paper is talking about both the need for a theory of life, but also kind of if you want to set that need for a theory of life aside and still make progress in trying to detect life, one thing that you should do is try to focus on features of life which are unambiguously associated with life. So we only see those features when there's life. So kind of the canonical example for this is something like DNA or RNA. We only see DNA or RNA when they're associated with life. We don't see those things outside of life. And so we talk about the need for kind of more unambiguous features of life. And that's one way kind of that we think that progress can be made in astrobiology. So another way, for example, might be looking at really complex chemicals, whether or not those are kind of these polymers. Or, maybe we can come up with some new ways to think about identifying things like replication, which people think, again, might be a hallmark feature of life in a way that can't occur in non-living systems.
But I think about these ideas like, it takes in some kind of material from its environment, including energy. It has some kind of membrane that separates it from its environment. It does something, and then ideally has some kind of evolutionary process that's involved that allows it to change over time. But I probably just mashed together 5 different definitions of life there. I mean,
yeah, and that's kind of another point that we try to hit on in our paper, is talking about how we really shouldn't be discounting the idea of kind of it when you see it, but we should be thinking about kind of what that means, in kind of in a more rigorous way, because we think that there's a lot of kind of complex life that really we did decide that it's life by just seeing it. So if you look in kind of the history of discovery of new kinds of life here on Earth, for example, things like giant viruses or archaea or kind of weird, deep sea invertebrates, like some of those were actually identified as life, not because of looking at some result of a chemical analysis, but instead just by looking at kind of this holistic view of the creature or the organism and how it's behaving in its environment, and drawing the conclusion that, yeah, well, this thing matches kind of my intuitive definition of life based on my experiences with other macroscopic organisms. And so other people have written about this a little bit. It hasn't been super kind of well discussed in the literature, but I think that this is still a really important thing to keep in mind when we talk about detecting life.
Cole, how did you go about sort of studying this problem?
Yeah, so as Harrison mentioned a little while ago before we started talking, Harrison and I sort of went through grad school together thinking about the origin of life and thinking about the large scale patterns of life on Earth. And we were in the astrobiology community sort of surrounded by people that were talking about how they're going to go detect life on planets outside the solar system. And like, from our perspective, we were like, whoa, that's really amazing. I don't even know if we would recognize alien life, even if it was in a test tube right in front of us. And you're telling me you're going to see it through a satellite. Like, that's really spectacular. Like, what do you know that we don't? And so a lot of this work in particular was, not necessarily doing calculations or doing experiments. It was really like digging into the literature and talking to colleagues in the astrobiology community and outside the astrobiology community about like, what do you mean when you say you're going to detect life through this? And like, if you say, oh, if I detect these gases, then I'll go pop the champagne because we've detected aliens. Like, how are you going to convince the biologists in the department next door that you've actually detected new life? Like their standard of evidence for life form is like, you got to verify the 16S RNA, and you're telling me that like oxygen gas in an atmosphere out of 1 pixel is enough. So like, how are we going to square these things? And so really a lot of this project came from Harrison and I trying to think like, what evidence would we need that would sort of convince all of the stakeholders in this field that we've actually detected life? And the conclusion we came to was like, we don't think that the way we're going about this right now is ever going to produce that evidence, which, is challenging as people that really are interested in life in the universe and how life could be different than Earth life and how common it is. It's not fun to land on the conclusion of like, this isn't working. But, I guess that's part of the nature of science.
Yeah. And at the same time, I think that like part of the reason that we decided that we wanted to write this paper is not because we want to disparage anyone or we want to discourage anyone, but because like we want the community to kind of come to a consensus that, yeah, these are the problems in the field right now, and try to come together and think of ways of how can we overcome those problems.
But we've seen this problem happen before. When we think about how inconclusive the Viking experiment was, the Allen Hills meteorite, the discovery of phosphine in the atmosphere of Venus. I mean, we've had 3 examples where someone has said, we found life, and the rest of the community has said, I'm skeptical, is the nice way of putting it. And these things are right here. And so when we think about what it's going to take to make that same kind of conclusive evidence on some world that is many light years away, as you said, you're looking at 1 pixel. But, one field of thought is that it is going to just be overwhelming, that there would be a signal. I mean, obviously, if we see a technosignature, then that's overwhelming. They're sending us a signal, we're alive, hello, here's what our DNA looks like. Great, conclusive. But even so, like an overwhelmingly active biosphere, would that give, like, do you think there's a place where you could get to this?
Yeah, so I'll jump in and say, like, I think the point about technosignatures is exactly what Harrison was saying earlier about, like, unambiguous signs of life, right? Like, we sort of, in the paper, make this maybe funny analogy to the movie or the book Contact. And we talk about, like, there are abiotic sources of radio waves, but there are no abiotic sources of the Olympic Games, right? You get the Olympic Games beamed back at you, and you found life. That's very different than an ensemble of gases like methane and oxygen in its steady state with each other. That is a much more difficult question to answer. And part of the problem here is we're learning more about what life is and what it can be and how maybe other biospheres might be different. But we're also becoming more and more aware, thanks to like the exoplanet revolution and a lot of progress in planetary science, that like there's a huge diversity of abiotic worlds that we really don't understand as well. And so I think short of a technosignature, and I'll be specific what I mean by technosignature, sometimes people talk about like chlorofluorocarbons or pollution in atmospheres. No, I mean like directed sort of radio transmission, contact, that kind of stuff. I think short of that, when we're talking about outside the solar system, I don't see how we get to overwhelming evidence, right? And I think Harrison can talk a little bit about like how we were inspired by these challenges that are present even inside the solar system, where we could potentially have a lot more information.
Yeah, one of the things that we kind of lean on in the paper is, again, a lot of this work was kind of digging into what people have talked about in the past and trying to synthesize a lot of different ideas from people that came before us and talked about, various aspects related to astrobiology, maybe with different goals in mind. One of those was, Carl Sagan with colleagues wrote a series of papers in, I believe, the 70s about, would we be able to detect life on Earth? Can we detect life on Earth if we imagine that we are, people that live on Mars? And basically the conclusion of the paper at that time was it's extremely difficult to pin the observables that we see in Earth's atmosphere on life. And even if you go down to getting imagery of Earth's surface, you're going to need extremely high resolution imagery before you can be certain that the observations you're making are unambiguously associated with life, as opposed to maybe having some kind of abiotic alternative explanation. And I believe in the paper they talked about needing imagery on the scale of 100 meters per pixel, which is basically as good as the best imagery we're getting of some of the moons of Jupiter, for example, like imagery we're getting of Europa from spacecraft that we've had in orbit around Jupiter, or spacecraft that we have in orbit around Saturn, looking at images of Enceladus, for example. And so even if we imagine we had a spacecraft hovering around another planet, getting imagery at the scale of 100 meters per pixel, if what we're seeing from this past work done by Carl Sagan and colleagues, saying that if we had similar imagery of Earth, we still wouldn't be 100% sure that what we're looking at is life. It's hard for us to imagine how we're going to make kind of conclusive claims from here on Earth, looking all the way at planets that are, as you said, at closest light years away.
When I think about the search for life on Mars, like originally we had that Viking lander, the Viking experiment. It was very ambitious, and yet it led to a very inconclusive result that people still argue about to this day. And so NASA sort of went back to the drawing book and said, okay, no, wait, we're just going to do this in a very incremental approach. We're going to first look for evidence there was ever water on Mars. Then we're going to look for evidence that water was acting on Mars for a long period of time. Then we're going to see if there was the conditions for life. And then, maybe with the Mars Sample Return mission, or maybe when humans go to Mars, that we're going to go actually look for either past or current life on Mars. It is a 20-year, 25-year journey to very carefully build up the science case. And I think it feels to me like astrobiologists are trying to follow the same pathway with James Webb, with Ariel, with other methods of analyzing the atmospheres of exoplanets. They're going to do it very slowly. They're just, we detected methane, right? We detected carbon dioxide. Do you think that's going to get them there? Or is there some radically different process to arrive at a destination that gets you some results?
So one of the takeaways that we had once we were, writing this paper was that it's clear, just like in a lot of organizations that receive money, have obligations to various stakeholders. And this may sound like a very political answer, but part of the problem with, this kind of slow timeline for detecting life in the field of astrobiology has to do with wanting to make sure that we don't accidentally prove that life can't exist on another planet, because that would kind of jeopardize the justification for receiving money in the future. If we could very clearly make a determination that there was never life on Mars, a lot of astrobiologists probably wouldn't want to run that experiment or make that observation, because there's a chance that it could come back saying, yeah, there was never life on Mars, and all of a sudden a lot of work that you're doing, maybe it's a lot harder for you to justify funding. And so there's this whole aspect from that end about the problems with trying to move ahead too fast and claim that you can definitively determine whether or not life is there based on a specific kind of experiment. And so I think that motivates kind of this gradualism that's kind of pervaded astrobiology. At the same time, I think that there really are a lot of unknowns about how do we make progress because of this problem that Cole talked about a little bit earlier, where we don't really know what it is that we're looking for. And so the best we can do is make these small steps for things which we think are really important, but we still can't really place clearly in context because we don't have the context of a theory of life like we do for theories of other things. I don't know if you want to add to that, Cole.
Yeah, I'll just add in that I think, as Harrison pointed out, this like slow, gradual process has really been internalized, specifically in the Mars community. There's like a whole community of scientists that are just like really focused on Mars, but also generally within the solar system. I think the planetary scientists that work on this sort of realize that there's going to be a slow process here, and that has pros and cons. I think an upside is it allows us to think carefully about what experiments are going to give us the most information and reduce our uncertainty the most, and how to plan for those. A downside is I think we end up in sort of silly circumstances where, for example, the Dragonfly mission to Titan, the moon of Jupiter, is classed as like a prebiotic chemistry mission.
That moon of Saturn,
moon of Saturn. Thanks, Harrison. And, we don't know if there's life on Titan or not, right? You can't really do a prebiotic chemistry mission on a world that might be alive. And so, even some of these more slower, more methodical approaches run into this problem of like, well, if we don't know if there's life there or not, that really changes our scientific objectives. Yeah, the last thing I'll add, just maybe more directly to your point about like what JWST and these future space telescopes will be able to do, a key feature of exploration in the solar system is we can land on the planet and we can do experiments. And it might take a decade to plan the new experiment and get it there, but a decade's about the right time scale for a scientific career. For planets outside the solar system, we don't have access to what Harrison and I refer to in the paper as ground truth. Like you don't get to land and figure out exactly what the surface process is. You get details from far away, and you never get to do an experiment that helps you resolve those.
I mean, when I think about that exploration inside the solar system, like one possibility, the more high risk maneuver you could do is take some really complicated chemistry analysis lab to the surface of Mars and just shovel regolith into it and then break everything down and just analyze the complexity of the molecules that you find. And if you're starting to find a lot of really complicated molecules, that's an indication that there is life that is generating harder to sustain, more complicated molecules. And so there's a case to be made for doing the high stakes version of this in the solar system, as you said, because you can do the get it onto the ground. But you can't when you're analyzing the TRAPPIST system. And so it feels like it's two completely different pathways, one which is within the solar system and one which is outside of the solar system. And they can't be approached in the same way.
Yeah, I think that's absolutely right. This idea of like what we can do in the solar system, I think we just have more access to those worlds. And like I have a lot of sympathy for my astronomer and exoplanet colleagues, right? Like they're doing incredibly difficult things. And so are the planetary scientists that are actually putting these instruments on rockets and sending them to other worlds. Like it's a remarkable technical achievement. But I think there's been this sort of like background belief that like, yeah, whatever we can do in the solar system, we'll eventually be able to generalize out to stuff that we'll be able to do outside the solar system. And I think what Harrison and I are trying to point out here is like, we shouldn't assume that's a given, that we're going to be able to like be really confident in life detection outside the solar system, short of maybe sending, a spacecraft to another star, which, I think we can for now say that's more of an economic and political impossibility than a scientific one. So yeah, Harrison, I don't know if you want to add anything there, but I think this is a really important point that like, actually these types of exploration are very different in nature.
Yeah. And I think, Fraser, your point as well about, couldn't you just send a package to another planet and do some really kind of complex suite of analyses to give you some really nice information about kind of clarifying what are the interesting things that are there, whether that's life or not. I think that a lot of people do want to do this kind of thing. And I think there's, Cole is involved with some other research that is more along the lines of doing these kind of complex chemical analyses and trying to understand what that means for the complexity of the underlying chemistry and if that says anything about life or not. So people are thinking about this kind of thing. I think that, the underlying problem is still that we don't have one experiment which can kind of give us that definitive answer. And so even if we do a really cool experiment which can inform us about kind of new chemistry, whether or not that chemistry is associated with life is still going to be an open question. And it's hard to understand how we're going to resolve that without progress kind of being made on the back end in terms of, theory of life and kind of more consensus around what it is that people are talking about when they're talking about life.
And so like researchers who are looking at this from the technosignatures side, they make the case that if you do want an unambiguous signal of life in the universe, that you go for the technosignatures. But that's ridiculous. Is sort of like that's crazy to go look for intelligent aliens. Like that is, no one looks for aliens. That's UFO stuff, right? And the SETI's had this very negative connotation for decades, and finally it's starting to get some appreciation and some funding and recognition within the astrobiology community. So how do you feel about that tension? Like as you said earlier, if you have the Olympic Games being back at you, then there's aliens, but that's just one. There are dozens of ideas that have been proposed of varying degrees, but most of which are conclusive, and yet it's still seen as it's the appendix, it's the kids' table. Like you don't have these conversations seriously with the rest of the astrobiology community.
Yeah, I think that the perception in general, like you're pointing out, Fraser, recently has been changing. And even within, kind of serious scientists, serious astrobiologists, the perception's been changing. If you like, for example, one of the biggest, gathering of astrobiologists happens at this conference called Astrobiology Science Conference, which happens every 2 years roughly. And I would say I've been to the past several of these conferences, and especially the past one or two of them, there's been a lot more interest and a lot more time and, presentation time, presentation space given to people working on things related to technosignatures, things related to how might we detect, life that's not simply microbes, but life which looks more like you and I. And so I think that is really changing. One of the things we try to talk about in our paper is, this idea that technosignatures are a reliable, good signature of life because, like Cole was mentioning earlier, the most parsimonious explanation would have to be intelligent life. You can't imagine, an abiotic alternative that's easier to explain how it would generate a particular signal, whether that's, radio signal or whether that's, lights going on and off on another planet or whatever, than thinking about intelligent life. And I really hope that the perception kind of continues to change and that the idea that, technosignatures are a viable path forward, continues to develop, because I really do believe that technosignatures, out of all the kind of different possibilities we mentioned in our paper, technosignatures are really the only one which would allow you to definitively detect life on an exoplanet. And so I think that really is the path forward for people that want to determine whether or not there's life outside of the solar system.
But if the scientific community presented the chlorofluorocarbon finder or the Dyson sphere locator, or the antimatter drive detector, they would be laughed at. Right? And so they live in the shadow of these other observatories and say, well, Webb is amazing for looking at the atmospheres of exoplanets. And by the way, if we're really lucky, would it be all right if we checked for chlorofluorocarbons? That seems backwards to me.
Yeah. So I think that I partially agree, but I think that there also is kind of a subtle distinction between the kinds of technosignatures that you're talking about. For example, chlorofluorocarbons, I think, is a technosignature which a lot of people could be behind, because we know that it's possible to make chlorofluorocarbons. We know that intelligent life makes chlorofluorocarbons because it's happened here on Earth. And so I think you could get more kind of agreement and support behind a mission to go look for chlorofluorocarbons. When you're talking about something like Dyson spheres, now you're already kind of in the regime of, this seems like it's something which should be possible, but we don't know whether or not it is possible, because, we're intelligent life and even we haven't made something like this. And same with kind of an antimatter drive. Because maybe there's nothing like that can possibly exist. We don't know that it can exist yet. And so I think that classifying kind of technosignatures into the categories of, hey, it's a technosignature, we know it's possible to exist because we've made it here on Earth, versus technosignature that we think should be possible, but we've never observed, I think you're still going to kind of get camps falling into how many resources to devote to these two different kind of categories.
Sure, but I think if you ask the entire astrobiology community or the folks thinking about technosignatures and said, just give us your top recommendation, give us the decadal survey of technosignatures, there would be one thing, like maybe it's going to be radio dishes around the world scanning every single star within a certain radius for signals, right? Like they would have a preference, and yet right now they'll get laughed at. And so they have to, we report on this stuff all the time. They're amazing, clever, resourceful ways that they get access to data when someone's looking at pulsars, right? So they can just check to see if there's a signal from an intelligent civilization somewhere in the field of view. That is the perspective. That is, I think, the way they're seen right now.
So one thing I'll say about this is I do think you're right that this is the perception of them, especially outside of the astrobiology community. I think there are serious thinkers in the astrobiology community, as Harrison was pointing, and a growing number that are realizing like this actually might be a really promising way forward. Or it might even be something that we really need to spend a lot of time on, sort of making sure we've exhausted the low-hanging fruit in the space of technosignatures first. And the way I usually sort of try to get people on board with this idea, which, is a little bit easier when you're already talking to astrobiologists, right, is to point out how difficult the problem of using atmospheric gases to detect microbial life is, right? So we don't know exactly what life is, but most people would agree it's got to be something that's sort of undergoing something like Darwinian evolution or selection. And it should probably be doing that for a really long time, like on the time scale of something close to our planet, right? So what you're telling me is we're looking for sort of an evolving lineage that's a couple billion years old. And you're telling me we're going to look at the concentration of gases in an atmosphere. And from that, you're going to conclude that there was a multi-billion year lineage of evolution happening? Like that, I'm not saying it's impossible. I'm just saying that's a very difficult problem. And so, if you think we're crazy because we're saying, hey, maybe we should look for radio signals, I'm going to sort of turn the tables and say, mate, you're looking for microbes with gases in an atmosphere. Like that's just as hard, if not harder. I think there is this perception. I agree. And I think it's really difficult, right? The astrobiology community is this strange community where there's a bunch of people looking for alien life. Almost no one ever says alien, right? Like we use lots of different euphemism. We say life in the universe, life beyond Earth, non-Terran life, all these words where we're like trying to be very careful to not be categorized into the crazy bin. And I think some of that's justified. People have careers to focus on, and there's a level of seriousness and, some challenges in the current media ecosystem. But at the same time, like we're looking for aliens. We want to know if there's life on other planets. Those are aliens, right? And so I think being a little bit more honest about like how difficult this science is, and that there are some really good ideas, but we also need to be open to a lot of other ideas from outside the community is really important.
I was just going to kind of add on to that, because I think you had a really good point, Fraser, when you're talking about like, maybe we should be making kind of decadal surveys for technosignatures. That sounds like a really cool idea, I think. But I think that goes back to kind of this earlier point of, the problem, maybe one of the problems with technosignatures when you're talking about how science is traditionally done is that they have a higher chance to give you kind of a yes or no answer. And that no answer can be dangerous when you're talking about, keeping the excitement going. And so we see this even with a lot of really high profile funded missions, which, generate great media hype with astrobiology related discoveries. Those missions usually aren't actually astrobiology missions. They're actually geology missions, or they're actually astronomy missions. If you look at the Mars rovers like Perseverance, Curiosity, the main goals of that mission aren't astrobiology related. They're geology related, because we know that we can make some progress on the geology aspects. And same with JWST. It was developed, not as a mission related to looking at exoplanets. It was developed as a mission related to other really interesting, astrophysical phenomena. And it's kind of a side goal to generate some new information and new observables related to astrobiology. But it's very intentional that those aren't astrobiology missions, because there's a danger that, you'll come back with kind of this negative result or this inconclusive result. And that's scary to a lot of people.
So, how do we make progress? They're obviously JWST right now, we're in the nascent stages of observing atmospheres. Ariel's coming up in 2028. It's going to observe many more atmospheres. The Habitable Worlds Observatory is in sort of the planning stages now, and it will be just a beast of exoplanet analysis. But if it launches and we don't have this theory of life yet, what is the way that we get the field ready for when these observations are made?
I think that, and we talk about this in the paper, we sort of highlight 4 ways that we think the field can move forward in the face of this problem, in the face of the fact that like we don't have a theory of life, and we want to understand the distribution and diversity of life in the universe, right? So one way is what we were just talking about, is technosignatures. As we've discussed, I think those have at least potential to be unambiguous in ways that other, gas-based, atmospheric-based biosignatures don't yet. The other ways to move forward are to continue studying the diversity of life on Earth, right? This maybe sounds like a little boring for astrobiologists, but we are constantly surprised by the things that we learn about life and how different it could be, and how different it is even on Earth. And so for example, if we're interested in understanding the distribution of complex organisms, there's like really great work on like, why is it that eukaryotes are complex multicellular life forms, but prokaryotes, even though they evolved multicellularity, never became complex in the way eukaryotes did. Like, that's sort of a foundational puzzle in biology. And understanding the answer to that question would really sort of help us understand how common we should expect complex versus microbial life in the universe to be. So technosignatures, studying life on Earth more, searching for life in the solar system. I think because of exactly what we described, even though we have these sort of traumatic experiences associated with the Viking experiments and the Allen Hills meteorite, I think that because we can go to these worlds, we can design experiments, we can even do experiments, we get more than just observations. We have the possibility to sort of resolve our uncertainty in these in the long run. And then the last piece, which is the piece that I'm most excited about, is actually trying to make life as it is not in the lab, right? So if we can create de novo life in like a controlled lab environment where we know that it's really like in a genuine way, like a second genesis of life, that we didn't just pull some genes out of a minimal genome and like make a synthetic cell, but actually like a new life form or a new biosphere, really, that allows us a way to experiment with what is possible, what the relationship between the abiotic condition and the biosphere is. And so those are things we can do in chemistry labs now, that will help us not just like figure out what's possible for life to be, but also like rule out sort of ideas of like what abiotic signals could look like. Because it might be the case that it's like, oh yeah, we did a bunch of experiments, and in this condition, even though we tried to sterilize it and make it abiotic, we always found life emerged in that system. And so then it'd be like, oh, okay, like that's a great target for searches on other planets. So those are sort of 4 ways that we focus on.
Right. But that simple problem of just making life out of nothing,
Yeah.
right? Like all you got to do,
easy peasy.
If you want to make progress, you just need to solve one of the greatest mysteries in science, which is where did life come from?
Yeah, exactly. Yeah.
Yeah.
With this one easy trick.
Yeah. And while you're at it, figure out where the universe came from.
Right. But this is actually a really important point that I talk about both in this work with Harrison and some other work that I've done. Is like, the reason that it's important to focus on this making life in the lab is it actually sort of helps us close the loop in the scientific progress, right? So the challenges that we have with our observational approach to searching for life beyond Earth are that like we just don't really have great hypotheses, is what it comes down to. We don't have these observables that we know are unique to life, and we don't have a really good set of data that people would say like false positive signals. And so what we need to do is figure out how to couple our observational program, which is these mission-based large space telescopes and surveys, to an experimental paradigm that we can execute on here on Earth. And there's like a precedent for this in the history of science. So like in the post-war era, we realized because of inflationary cosmology that the very early universe was very hot and very dense. And actually that very hot, very dense setting was like exactly what was going on in our particle accelerators. And so we learned that like, oh, actually like a lot of large scale structure of the universe, we should be able to predict from our theories of particle physics. And also, if we make observations about the large scale structure of the universe, we can like help refine our theories of particle physics. So this like sort of closed the loop where we had this experimental paradigm in our particle accelerators and our cosmology observational program. What we need to do is sort of drive like a similar like closing of the loop in astrobiology, where we couple our observational program to experiments that help us refine our theories and our models together.
Is there like a good coupling between the biology community and the astrobiology community? I mean, there are definitely biologists working on this abiogenesis question, but I don't know if they're even sort of thinking about the astronomical implications of what it is that they're working on. Is that happening?
I would say it's starting to happen more. There's some people, and Harrison can sort of speak to this as well. There's not that many of us, but we're out here.
Yeah, I think that, this is also something which has been coming into focus the past, several years, I would say, which is trying to bring more people together who have kind of different specialties to work on this related problem. And And like, obviously that's going to be kind of a strategy for any kind of interdisciplinary problem in science or elsewhere. But yeah, I mean, in astrobiology, historically, it's been a lot of, people with backgrounds in physics or astronomy working on the problems. But I think these days there's been a little bit more focus on trying to bring people who focus more on, chemistry or biology, biochemistry. I want to just go back to your point, though, Fraser, a little bit more directly about kind of these future observatories and how to make progress with those, because I think that's also an important question. Is like, if we're saying that we can't detect life, no matter how hard we try with these expensive observatories, what are we doing? And just like Cole was saying, I think that there's a lot of value in trying to understand the diversity of processes, whether or not those processes are associated with life. And so we can do that on Earth in the lab. But we can also do that with, exoplanet observatories to get a better idea of what does the diversity of exoplanets look like, and try to get a better understanding of even things like, how many planets have atmospheres or what the average density of planets are as you look, in terms of distance from their star. I don't think people really fully grasp the, difficulty of doing something which sounds as simple as determining whether or not an exoplanet has an atmosphere. As we've learned, recently, when the TRAPPIST planets were first discovered, they were kind of pitched as this like kind of idyllic new system of planets. They all look beautiful in different ways with their, atmospheres, and we can imagine different kinds of, geochemical or maybe even biological diversity. And then it's come to light recently with new observations that maybe these planets don't even have atmospheres. And so there's a lot of big problems to overcome, that can be at least addressed in part by creating these new observatories, which kind of have different focuses.
When we look around us here on Earth, the question of like, is there life on Earth is a ridiculous question, because you don't have to go very far, even, you're looking at your own hands, right? But there is just life everywhere. like it's filled every possible nook and cranny, every niche. And yet, when we look out in the universe, it feels a bit like an untouched wilderness. Like we don't see glaring evidence, like we don't see trees on Mars, we don't see, floating creatures in Venus, we don't see European space whales, right? The obvious signs. And so whatever it is in the solar system, it is very rare, possibly non-existent. But do you think that indication, when we look out into the universe and we just don't see anything that's obvious, is a hint?
Yeah, so I think that, I'm going to push back on the framing of your question a little bit. I don't know that there's not life in the solar system, right? I don't know that it's not obvious. I think Mars we've looked at pretty carefully. And, if I was a betting person, I'd probably bet against life on Mars, but I might bet lunch, but not a car.
But no trees on Mars. I'm saying no obvious life on Mars.
Yeah. There's no trees. We don't know what it's like under the surface of Europa or Titan, or what the oceans of Titan have for us, or what's under the ice at Enceladus. And so I think what we need to do is figure out a way to systematically try to answer that question. I think, one of the challenges in this area is our prior expectation for whether or not life should be on a planet is completely unconstrained, right? Let's say we definitely think it's here on Earth. So that's one example. We think it's probably not on Mars, right? We'll just give that. And let's say we don't think it's on Venus, right? Phosphine aside, let's just say like, all right, like it's too hot and it's too brutal there. Okay, so let's say the higher end of our probability is 1 in 3 planets. That's still pretty high, right? And that hasn't even, we haven't even tried to rule out what's going on these icy moons. So I think the most that I could say is our uncertainty about whether or not there should be life on other planets is perhaps one of the most uncertain things in science, right? Like the question of how common is life in the universe is a really important question about the nature of the universe. It's basically a cosmological question. It's as fundamental as, why is there mass and not antimatter? And we are nowhere near close to having any idea what that value should be or what the explanation for that is.
But if you were on a boat and you arrived on an island and there was, it was volcanic rock, not a single palm tree anywhere, maybe a couple of seabirds landed on top of it, you would have some opinions about that island, about how old that island was, right? You would see the lack of life would be a signal to you that would say, okay, this was probably formed fairly recently. There's no life here because it just hasn't been around long enough for it to settle. And yet, if we think about perhaps advanced civilizations have been around billions of years before we were. The universe was habitable several billion years before Earth was habitable. And yet we don't see a fully populated, the Fermi paradox. Where's everybody? So do you think that gives us sets any kind of constraints on how much life there is out there in the universe?
It's hard for it to give us any constraints because it's such a hard kind of conceptual problem. I think even thinking in analogies makes it hard. Going off this idea that maybe, there were billions of years before Earth even existed, that there was time for other planets to develop intelligent life. The science says that should be possible. And so maybe there's other intelligent life out there that's billions of years older than us. And then it becomes a question of, okay, even if that life is out there, and even if we knew for sure that that life was out there and we just didn't know how to find it, trying to figure out how to find it would be, another problem that's even hard to kind of figure out where to get started. It's kind of like thinking about if I sent you back in time to the earliest humans and you dropped your cell phone on the ground, would they be able to look at that cell phone and say, this is evidence of life? Because the way that we communicate and the way that we live our daily life is already so different from the way that, humans in early history lived their lives. The idea of this brick being something that allows me to talk to people on the other side of the world is such an absurd concept that it wouldn't even enter people's mind as a possible hypothesis. And so I think that that's possibly at play, thinking about how we detect life on other planets outside the solar system that have been around for a lot longer, which is like, how do we even get in the right mindset to imagine the possible hypotheses of how we could be detecting that life? Because chances are they're not, setting up AM, FM radio stations to talk to each other. They're doing it in a way that we can't even imagine.
You've said there's like a bunch of problems and you've proposed some solutions, and those solutions are being acted upon in various ways. So what are some stuff that you would like people to sort of keep an eye on, to be excited about, to help gain progress in these challenges?
Go ahead, Cole.
In spite of my earlier comment about it being a little confusing to be a prebiotic chemistry mission, I'm extremely excited about the Dragonfly mission to Titan. I think it's going to be one of the most informative missions that NASA has done in a really long time. Titan's a great place to go look for life. It's the only other place in the solar system with beaches. It's just that the sand is water ice. The ocean is methane, and the atmosphere is also methane. But that three-phase equilibria is really, from a chemical perspective, very exciting. So I'm really, really excited about the exploration of these icy moons. I think we're going to really learn a lot about planetary science, and also potentially about astrobiology. And outside of that, I am excited about these telescopes, right? Like, the things that we can do with JWST are remarkable. They are remarkable technical achievements. And they're going to help us really understand more about like the diversity of possible planets. I think the main thing I'd like people to take away is that, learning more about planets is not exactly the same as life detection. But it's really an important piece of the puzzle. And then outside of that, the last thing I'll say is I think there's really amazing innovations happening in robotics and computation in the field of chemistry that I've been sort of close to in my career. And I think people are maybe unprepared for how different the future of what we can do in the lab is going to be from what we have been doing for more or less the last 100 years.
Yeah, I mean, I'll echo everything Cole said. I think that, it sounds cliche, but the kind of what's happening recently with AI, and if you think about how to pair that with robotics and chemistry, starting to explore chemical space and get a lot more chemical data will help, people who do focus more on theory come up with better hypotheses about how things work, and that can really lead to a lot of big advances in kind of the theory side of things. I think from the experimental side of things, I'm really excited about the solar system. I think that despite all the missions that we've sent in the solar system, there's still so much to learn with really kind of quote unquote like simple experiments or simple missions. For example, when I say simple, I don't mean it's engineering, it's easy, but we can imagine how to do it at least. So, if we could just send a camera to the ocean of Enceladus or the ocean of Europa, the amount of new scientific knowledge that we would gain for that investment, and already we know kind of how to get there, that's kind of immeasurable. So it's totally possible that we do have macroscopic life in the solar system, and all we have to do is look in the right place, and we just haven't looked in the right place yet. We haven't actually sent a camera anywhere that there's liquid water in the solar system besides Earth, and everywhere there's liquid water on Earth, there's life. So it could simply be that maybe there's octopi and there's sharks and whales floating around, and we just haven't bothered to stick a camera down there. So I think that there's a lot of really kind of low-hanging fruit in terms of progress that can be made just by sticking to the solar system.
Well, Harrison Cole, thank you so much for your time today, and hopefully someone will get to the bottom of this and find life sooner than later.
Thanks so much, Fraser.
Thanks a lot.
I hope you enjoyed that interview. It was a lot of fun. Now I'm going to talk some more about this search for life in the universe, but first I'd like to thank our patrons. Special thanks to Dougie Stewart, Stephen Krasaki, David Richards, Mark Anstis, Joel Yancey, Antonio Lofilar, Dustin Cable, Vlad Shiplin, Monzo, George, David Gilton, Andrew M. Gross, Jeremy Mattern, Josh Schultz, and Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. A couple of decades ago, when I was first getting into this field, I had this really oversimplified view of what life was going to be. Like, as soon as we find the presence of oxygen in the atmosphere of an exoplanet, then it is definitive proof we found life, done. We know we're not alone in the universe. But we've seen that this problem is getting just more and more complex, that there are many more ways that abiotic methods can produce the same kinds of chemicals that biology can. And then we don't even understand all of the possible ways that life could be. I mean, there's life as we know it, but what does life as we don't know it look like? And so would we be missing those signals for life that's all around us, right in front of our faces? And so over time, like both of these parts of this problem, the true nature and challenge is becoming more and more revealed to me. And I realize just like how much work is yet to be done. Now, I had a very similar conversation with a researcher about the hunt for abiogenesis and sort of what implications that has on the future of life in the universe. So that's with Dr. Sucrit Ranjan. I think you'll really enjoy that conversation. And then another one that I had was with Dr. Adam Frank, and we were talking about his new book, The Little Book of Aliens, and we talk about a lot of those same topics as well. So if you want to think more about the search for life in the universe, here's some more places to start. All right. We'll see you next time.